Okay. The very last density problem we're going to work on before I get to start seeing you guys back in school. Hopefully I'll be seeing you guys back in school. Is this density problem. The samples that I have here are one very large metal sphere and then one very small metal sphere. Okay. However, there's a little bit of some trickery going on here. Right. Let's go ahead and measure the mass of both of these steel balls. I think they're steel. They look to me like stainless steel, which is another alloy of steel. An alloy is just a mixture of metals. When we talk about steel, we're talking about the metal iron. There is no metal element called steel. There is a metal element called iron. Steel is primarily iron, but it's a steel because it's mixed with other things. It's an alloy of iron. Anyway, all right, we're going to zero this guy out. Now you're going to have to write these down, these masses and the other things we're going to need to know. So let's see. If I put this sphere directly on the balance, it's going to roll off. So what I'm going to do is I'm going to put a little washer on there and then put the sphere on the washer. It'll keep it from rolling. Now this weighs 7.86 grams, and I could write that down, and I'd just have to subtract that away from the total mass. But these electronic balances make it nice. You just hit that 0 or that tare key. It re-zeros the balance, or tares the balance, T-A-R-E. We talked about that the other day. And now when I put this small sphere on there, the weight that it says here on the display, 128.78 grams, is the mass of just the sphere. It is not the mass of the washer also. 128.7, well, now it's saying 79 grams. So let's go with that, 128.78 grams. Take that off, put it aside for a second. All right, with the washer on here, I'm going to tare it again so that the balance says 0. I'm going to take this large sphere and put that there. Now, it weighs a little bit more than this small sphere, but not a whole lot. Its mass is 135.90 grams. So let's write that down also. Okay. So we can get rid of this. We're done with that. All right, we know the mass of each of these objects. All right, they're nearly the same. They're only about 7 or 8 grams difference from one another. And 7 or 8 grams is, you know, maybe the weight of, I don't know, the 1 or 2 caps from these dry erase marker pens. All right, it's not a lot. All right. You know, the obvious issue here is that this stainless steel ball is mostly empty inside. It's probably filled with air, so it's not empty, but it's not metal through and through, whereas this guy is. Anyway, if I want to compute the density of these two objects, I need to somehow determine their volume also. Now, this is a nice regularly shaped geometric shape. It's a sphere. And on one of the videos I asked you to watch yesterday, I think it was video 3, the fellow there was solving a problem dealing with sphere. So go back and look at that. Anyway, for a sphere, what we need to know to get its volume is its radius. Well, the radius is the distance from the center of the sphere to the outer edge. Now, there's no way for me to get my verniers to just be lined up with the center of the sphere. You know, there's no way to really judge that to get the radius directly. So the best I could do here for you guys is to measure its diameter. You'll have to take this measurement and cut it in half. All right, this is the diameter of the small sphere, 31.72 millimeters. So the small sphere is 31.70, oh, this is saying 73 millimeters. Now, you want to change that to centimeters because when you do the calculation, you want the final volume to be given in cubic centimeters, not cubic millimeters. So change millimeters to centimeters. You know, for that, we ought to go back to something we looked at a long time ago. And that's this guy right here. All right. How do I go from millimeters to centimeters? Remember this metric ladder? All right. Millimeters to centimeters is just one jump. Milli is 1/1000th. Centi is 1/100th. It's one jump. So anyway, go back and take a look at that again. So 31.73 millimeters, change it to centimeters. Yep. And now this guy, this big sphere. Let's see if I can't wrangle this. This might be tough. Also, just because these jaws don't extend all the way to the edges of the ball, into the sphere. All right. If I clamp it this way, obviously the jaws of the vernier of the calipers aren't touching the extreme edges of the sphere. So what am I going to do here? What will I do? Well, let's see. Now, if I were just to take a ruler and sort of eyeball it, I'd get a number. But it wouldn't be very accurate now, would it? All right. Let me see, where did I put that little washer? I don't want this thing rolling all over the place here. Yep, there it is. Even that's not going to work because that'll raise it up off the tabletop. So I'm going to just attach it here. A piece of table, keep it from rolling. How can I measure the height of this sphere as accurately as I can? Let's try it this way. I'm going to set up this ruler just behind here, and let me see, give me a second, hold on. Now I have both the sphere and the ruler behind it, both sitting. You could see my reflection in there. You could maybe if we could do this. Take a zoom in over the top of the ball, and maybe line it up with one of the lines on the left side of the ruler, because the left side is the metric side. Those are centimeter markings. You can see the 12, the 13, the 14. The other side, the 5, the 6, those are inches. We don't want that. But how do we line it up and read the correct line? Depending on the angle we read it at, you could go down there by 11. If we look at it from a slightly different angle, we could read it up to about 12. Right? Actually, when you take readings of this sort where you have this kind of difficulty lining up lines on your measuring device, you're dealing with a type of error in measurement called parallax. Yeah. P-A-R-A-L-L-E-X. Parallax error. Parallax error. It's P-A-R-A-L-L-A-X. Parallax error. All right, boys and girls. I played around a little bit trying to figure out how we could easily get a nice reading of the diameter of this. And I came up with an idea that just a whole lot easier. I could have played around long enough and probably come up with something here that I could use to do this. I just don't have all the proper measuring tools here available to me. I do have this though, and I'm going to use this instead. So you're going to have to think about this, go along for the journey. All right, here I have measuring tape. It's the kind that a tailor, somebody who alters clothes or sews clothes, would use. You measure maybe around your neck or the length of your arm or around your waist or something like that. It's a flexible, but not, it doesn't, when you pull on it, it doesn't expand. It's got a very good stable length to it. It won't stretch out when you pull on it. All right. But it does bend. And what it does bend around is the sphere. So I'm not going to measure the diameter of the sphere. I'm going to measure its circumference. The circumference will allow us to figure out what the radius is. All right. What is the relationship between the circumference, right? The distance around the outside of this sphere is the distance around a circle, so it's the same sort of thing for a circle and for a sphere. What is the relationship between circumference and radius? Circumference equals something something with the radius in it. Anybody recall? How about circumference is 2 pi times the radius? Exactly what it is. Now, how do we take this equation and do a little rearrangement so that we could say that the radius, which is what we need to get the volume, the radius is equal to what when I rearrange this equation? Well, how do you get r by itself? Divide both sides by 2 pi. On this side, the 2 pi cancels. And we're left with r on this side. On this side, it's the circumference divided by 2 pi. All right? All that great math that you've been taught. See, this kind of stuff I could remember maybe 6th, 7th grade, 7th grade, maybe 8th grade doing this. Started talking about circles. All right? So, you're going to want to write that down. We're going to get the radius of this guy by doing a little work, an end run around some measurement. Be nice if we could, measure across here, but I just don't have the proper devices. But anyway, all right. The tape measure here is marked off in centimeters along this edge and inches. This we're going to ignore the inches and go right with the centimeters. So I'm going to take this and wrap it around the fattest part of this, this sphere. All right. And what do we get? We're going to get a measurement of, give me a second here. Tough here to hold it. We're going to get a reading of, All right. Where does the edge of this tape, all right? The very end of the tape is the 0 centimeter mark. All right. So wrap it around. This ends up at what? Between, I can't even read it. I think what I'm going to do is stop the video and we'll take a reading of this and I'll just project it on the screen for you. But that's that. All right. When what I want you to do calculation-wise is to compute the density of this large sphere versus the density of this small sphere. Now remember I said that the masses of these are very, very nearly the same. They're only off by a couple of grams. All right. We're going to find, though, that the density of this sphere is much less than 1. All right, this is greater than 1. Why is the density of 1 gram per cubic centimeter important? Because that's the density of water. If it's greater than 1, the thing will sink. If it's less than 1, the thing will float. Will this metal ball float? Well, just look at its density.